Hello there, young physicists. Have you ever noticed how a playground swings back and forth smoothly? That graceful to and fro motion is a perfect example of what we call simple harmonic motion, or SHM for short. Here's a fun thought. Why did the pendulum break up with its girlfriend? Because it couldn't stop oscillating between states. Alright, now that we have your attention, let's dive deeper. Simple harmonic motion is a special kind of periodic motion where the acceleration of the object is directly proportional to its displacement from a central point. We call this central point the mean position, and crucially, the acceleration always points back toward that mean position. Imagine you pull a spring and release it. The further you pull it, the stronger the pull back towards the center. Mathematically, this idea is expressed as acceleration equals minus omega squared times x, where x is the displacement and omega represents the angular frequency of the motion. The minus sign? That's a little reminder that the acceleration always tries to restore the object to equilibrium. It's like a friend who always nudges you back home when you wander too far. For a spring mass system, omega equals the square root of the spring constant divided by the mass. Simply put, it depends on how stiff the spring is and how heavy the object hanging on it is. If we track the object's position over time, the displacement x at any time t is given by amplitude multiplied by the sine of omega times t plus a phase constant phi. This formula beautifully captures how the object moves smoothly back and forth as time progresses. But for SHM to hold true, certain conditions must be met. First, the restoring force must be linear, meaning it increases proportionally to displacement, just like Hooke's law. Second, if angles are involved, as in pendulum motion, those angles have to be small so that the sine of theta can be approximated as theta itself. And third, we assume there are no damping effects like friction or air resistance slowing things down, so the motion can keep going perpetually. So next time you see a child on a swing or hear the ticking of a clock pendulum, remember, you're witnessing the elegant dance of simple harmonic motion right in front of you. Welcome back. Remember our swing or spring bobbing up and down? Let's now look at how fast it moves and how it speeds up or slows down at different points during its journey. Here's a quick joke to kick off. Why did the SHM particle break up with velocity? Because velocity was always ahead by a quarter cycle. Velocity in simple harmonic motion is also periodic, but it's not quite in step with displacement. In fact, it leads displacement by a quarter of a cycle, or mathematically, by pi over 2 radians. The velocity at any time equals omega times the amplitude multiplied by the cosine of omega t plus phi. Because cosine is just sine shifted by pi over 2, velocity reaches its maximum right when displacement is 0, that's at the mean position, meaning the object speeds through the center most quickly. The maximum velocity, therefore, equals omega times amplitude. At the extreme edges of the motion, where the object is farthest from the center, the velocity drops to 0 momentarily before reversing direction. Acceleration, on the other hand, is still sinusoidal but always points opposite to displacement, pulling the object back toward equilibrium. It equals minus omega squared times the amplitude times sine of omega t plus phi. Notice how acceleration has a stronger dependence on omega since it's squared. This tells us how sharply the object's velocity changes as it moves. Both velocity and acceleration are simply time derivatives of displacement. First derivative gives velocity, second derivative yields acceleration. In short, if you imagine plotting displacement as a smooth sine wave, velocity is a shifted cosine wave, and acceleration is once again a sine wave but flipped upside down. Together, these relationships paint a complete picture of the rhythmic and elegant dance of SHM. Now, Let's talk about energy, because every physics class loves that word. Ever wondered how the energy of a swinging pendulum or oscillating spring changes as it moves? Here's a little energy joke. Why did the pendulum go to therapy? Because it had too many ups and downs with its kinetic and potential energy. In simple harmonic motion, the total mechanical energy remains constant throughout the motion, assuming no friction or air resistance. This total energy is the sum of kinetic and potential energy and equals 1/2 times mass times omega squared times amplitude squared. Simply put, the energy depends on the mass of the object, how fast it oscillates, and the maximum displacement it achieves. Kinetic energy, which is the energy of motion, is 1/2 times mass times velocity squared. If we substitute the velocity expression from before, kinetic energy becomes 1/2 mass omega squared times the difference between amplitude squared and displacement squared. This means kinetic energy is maximum at the mean position, where displacement is 0, and 0 at the extremes where velocity is 0. Potential energy, stored due to displacement, is 1/2 times spring constant times displacement squared. Remembering that spring constant times displacement squared equals mass times omega squared times displacement squared, potential energy can be rewritten as half mass omega squared times displacement squared. So, potential energy is 0 at the mean position and maximum at the extreme positions. Together, kinetic and potential energy continuously trade places as the object moves, oscillating back and forth within limits, but their sum, the total mechanical energy, remains a steadfast constant. Think of it as a financial balance. The pendulum is just moving energy between its kinetic checking account and potential savings account, never losing any money as long as there's no friction tax. Alright, now for a really cool insight. Did you know that simple harmonic motion can be viewed as the shadow or projection of uniform circular motion? Here's a little analogy. Imagine kids playing with a spinning merry-go-round, and the shadow of one kid's hand traces back and forth like a seesaw. That's SHM in disguise. Uniform circular motion is when an object moves around a circle of fixed radius a at a constant angular speed omega, measured in radians per second. Now, if we look at the shadow of this circular motion projected onto a diameter, say, imagine shining a light straight down, this shadow moves back and forth along a line just like our simple harmonic oscillator. Mathematically, the displacement of that shadow at time t is radius a times the sine of omega t plus a phase constant phi. This matches perfectly with the displacement formula in SHM. The velocity of this shadow is omega times a times cosine of omega t plus phi, exactly like the velocity we discussed in SHM. The angular frequency omega in circular motion acts just like the natural frequency in SHM. It determines how fast the oscillations occur. In fact, omega equals to times pi times frequency, where frequency is how many oscillations happen per second. This equivalence helps us visualize and understand SHM better. Instead of thinking about a complicated to and fro motion, picture a dot moving in a circle, with its shadow dancing along a line. That's the heart of SHM right there. Let's turn to some graphs now, because physics without graphs is like a pizza without cheese. Here's a joke. Why did the sine wave cross the time axis? To get to the other phase. The displacement time graph of SHM is a smooth sine or cosine curve that oscillates between plus and minus the amplitude. The shape repeats itself after a fixed period t, which equals to pi divided by omega. The velocity time graph is similar but follows a cosine function, leading displacement by pi over 2 radians. This means velocity peaks when displacement crosses 0 and zeroes out at the displacement extremes. Acceleration versus time graph also oscillates sinusoidally, but it's inverted relative to displacement because acceleration equals minus omega squared times displacement. So when displacement is positive maximum, acceleration is negative maximum, pulling the object back toward equilibrium. All these graphs share the same period, t, indicating exactly how long one complete oscillation takes. The amplitudes vary according to initial conditions, but the periodic nature and phase relationships remain consistent, helping us predict the motion at any instant. Let's apply what we've learned with a quick example. Imagine a particle moves in uniform circular motion with a radius a of 5 cm and angular speed omega equal to 2 pi radians per second. We want to find the displacement and velocity of its SHM projection at time t equals 0.25 seconds, that's a quarter of a second. Using our formulas, displacement x at time t equals radius a times sine of omega times t. Plugging in the numbers, we have 0.05 meters multiplied by sine of 2 pi times 0.25 seconds. Since 2 pi times 0.25 is pi over 2 radians and sine of pi over 2 is 1, displacement is 0.05 meters or 5 centimeters. For velocity v at time t, it equals omega times amplitude a times cosine of omega t. Substituting values, that's 2 pi times 0.05 meters times cosine of pi over 2, which is 0. Cosine of pi over 2 is 0, so velocity at 0.25 seconds is 0 meters per second. This tells us at a quarter of the period, the particle is at its extreme position, fully stretched out away from the center and momentarily at rest before changing direction. This perfectly matches the theory that velocity is 0 at displacement extremes. Let's wrap it all up. Simple harmonic motion is beautifully captured by displacement as amplitude times sine of omega t plus phase phi, velocity as omega times amplitude times cosine of omega t plus phi, and acceleration as negative omega squared times displacement. The total energy remains conserved at half mass times omega squared times amplitude squared. Remember, SHM is essentially the projection of uniform circular motion on a diameter, with omega determining how fast the system oscillates. Velocity and acceleration are always out of phase with displacement, creating that elegant rhythm in the motion. Energy continuously swaps between kinetic and potential forms, but the total remains a steadfast constant. And visually, displacement, velocity, and acceleration graphs are all sinusoidal waves with specific phase relations and equal periods. That's it for today's fascinating glimpse into oscillations. Physics becomes so much more fun when you can laugh at oscillating jokes and appreciate nature's rhythmic dances. See you in the next session.